seminar. Welcome everybody to the UVA Bosch Delta Lab Deep Learning Seminar. This is the first time that we're doing this seminar completely virtually, so you might have noticed there are a little bit of startup problems, but I think everything is working now as it should. Questions for people in the seminar, you can ask questions with the Q&A button, and then at some point in the talk we'll have a kind of a short break to look at those questions. And you can also upvote actually other people's questions if you find them interesting, so you can kind of prioritize the questions in case we have too many. And in the YouTube, you can also write some questions in the comment. We'll also take a look at them and see what comes up there. All right, so then it's my pleasure to introduce today's speaker, Jens Kober. Jens did his PhD at the MPI for Intelligent Systems and at the TU Darmstadt. And actually for his work in his PhD, he also got the George Girault Award for the best robotics PhD in Europe for this work. And actually this is also where we met because we were colleagues for a short while at TU Darmstadt. Since his PhD, Jens has done a postdoc at the University of Bielefeld and the Honda Research University jointly. And now he is an associate professor at the TU Delft. And Jens has, for his work, also received a couple of awards. So among others, the IEEE RAS Early Career Award and the ERC Starting Grant. So today, Jens will talk to us about his recent work on robots learning through interaction, or also just learning interactions. And Jens, it's really a pleasure to host you in this meeting, and it's thank you a lot for joining us in this experiment today. And please, the floor is yours.
Thanks a lot for the very kind introduction. Also very exciting for me, first time giving a talk or such a big talk virtually, so we'll see how it goes. Okay, so here a little clip of a recent very advanced robot, at least in terms of hardware, and can do amazing things like this backflip. What you can see in the video here is that a team of robot programmers was probably busy for a couple of months to do that, and even then something can go horribly wrong, even if just something little changes. So what makes tasks hard for a robot? Like, if you ask me, I come from a control engineering background, it's complex dynamics. So things like friction or force interactions, that's extremely hard to model traditionally and hence also to control. And there are a lot of uncertainties and variations, both in the objects the robot is interacting with, the environments that might change quite a bit. And usually we don't want to have a one-trick pony, but a robot that can do multiple tasks. So there are huge uncertainties and variations in all those. And if you then consider that a robot is supposed to interact with a human, that gets even worse. Now the thing is that it occurs in virtually all robot domains. So if you want to get the robots out from behind this fence and have an Industry 4.0 more flexible manufacturing kind of setting, then we suddenly get all those. If you think about natural environments, in a greenhouse, for instance, then we have uncertainties in the object and the environment, elderly care, household environments, and so forth. So then the obvious question is, wouldn't it be nice if we don't have to program our robots by hand, but rather that the robots could learn such tasks? So that's going to be the part on learning to interact. So indeed, there have been huge successes on machine learning and AI, and especially related to deep learning. Just a couple of examples here, but what makes them different to robots? So why don't we see as many cool success stories on robots learning, at least in terms of these type of interactions and physical interactions I was just talking about? If you take a look at these again, then you could say what works very well is perception or high-level reasoning if you have complete information of the system and the state. So what I like to say is it works really well as long as you consider the head of the robot. And for the body of the robot, so actually the movement, there's still some way to go. We took a look at that quite some years ago, and I think that actually still holds, so the particular challenges. Robot learning has to be applied to virtually all different kinds of robot hardware, but one of the common themes is that the learning needs to be safe with real robots. So you don't want the robot to damage itself, nor its environment, nor the people it's interacting with. So mistakes can be very costly, which also implies that you want to learn fast. So many modern machine learning approaches rely on big data, but that's something we often don't have in robot learning. So we want to be as sample efficient as possible. You could say we want to deal with small data. Unless you're Google, and then you can have a whole army of robots working day and night for a couple of months to learn fairly simple tasks. So the way to get around that is, as probably all of you know, incorporate prior knowledge in different forms. And I'll talk about a few different ideas today. And you don't want to do extensive hyperparameter tuning, again, in the vein of being able to learn fast. And then if you want to do control, you need to be able to do the computations in real time. So what we need are really domain appropriate methods for robot learning. And here's a quick example of something we did a couple of years ago, just naively applying DDPG, in this case, to a robot learning setting. The slightly different part here is that we assume that we don't have infinite memory, so we need to actually take care of limiting the replay buffer. So what you typically would do is just do a first in, first out. So that's here on the left. So in the beginning, episode 6, that still seems to do reasonably well. But then if we now, I need to switch off the mouse pointer. I think, yeah, if we skip forward a bit, then it starts to actually go wrong quite quickly. Why is that? Because some of the initial data we had in the replay buffer that is capturing the more general and wide dynamics of the system, it gets thrown out once the system learns what to do. And then in the end, doing this first in, first out, which you might think is a good idea because then you can really focus on the parts you're interested in, just horribly fails. And then the alternative we came up with on the right is just to retain some of the initial data. And we've tried a few other ideas on how to keep relevant information in the replay buffer in this case. So just to underline once more that we do need domain appropriate methods. For robot learning, there are very roughly 2 different types of learning we consider, at least for these kind of motor skills, for these kind of movements. So the first one is imitation learning, which is also very much inspired by how humans teach and learn. Teacher demonstrates a skill, and then the student, or the robot in this case, tries to imitate or mimic that. It tends to work well for fairly simple tasks. For more complex tasks, also a robot needs to practice, and that's indeed reinforcement learning. What I am now got interested in lately is how do we actually learn as humans, and how can we transfer that to robots? So if you take a look again at how humans teach and learn, you'll notice that there's actually a continued student-teacher interaction. In robot learning, what you see quite a bit, or at least in the past saw quite a bit, is that you provide some initial demonstrations, then you try to mimic that, and then you might need some reinforcement learning to fine-tune that. However, if you take a look at how, for instance, a coach here in the top example would teach a student, is that you also get additional demonstrations and other forms of intermittent feedback during the learning process. So not only at the beginning. However, that's one of the things that is largely missing in robot learning. And I believe there are huge benefits to that in terms of speeding up the learning process, which enables robots to learn more complex tasks, and which is hopefully also fairly intuitive for humans. And that's going to be the second part of the talk about how to best make use of human expertise during the learning process. So how to interact to learn. Okay, but first let me talk a little bit about how a robot can learn complex interactions with the environment and potentially also humans. I'm going to start with imitation learning, then switch to reinforcement learning, and then towards the end of the talk, I'm going to come back a little bit to imitation learning again. So what's the idea of imitation learning? It's really giving a demonstration and having the robot reproduce that, but not only reproduce it, but also to generalize. So in this example here, not only to directly play back the two examples it has seen, but also be able to cope with different positions of the glass of orange juice. Now, the question is, what do we actually want to imitate? So here we have a little red coaster and the orange juice. So, and the table. So it's the movement relative to the orange juice or the coaster or the table. And that's something you can't directly see in the demonstrations, but that's something the robot actually needs to figure out. And that gets even worse if you additionally consider that we not only have position control, but also potentially force control, because also there's some kind of duality that a force causes a change in position and the other way around, that a position causes a change in the force. So if you take a look at this little example on the bottom, if you push down on this kind of a sponge, you're going to observe both a force and a position change. And then the question is, again, which of the two do we want to imitate? If you always use the same type of object, that doesn't really matter. It only becomes relevant again once you want to generalize, to transfer it to, in this case, a different type of sponge. So what did we do there? So here's a simple task of flipping up some kind of a box. Let me try to find an object. So flip it up like this. And then the next step would actually be to grasp it. So that could be a helpful skill for getting it out of a tight drawer or something like that. So here we collect a whole lot of demonstrations. It might be a bit tiny to see. So we got a whole lot of different sensor data, both the positions and the force readings in different reference frames relative to the table, relative to the object. And then we want the robot to learn. So what do we want to learn? Actually, I'm going to consider the whole complex sequence as a sequence of different movement primitives. So kind of elementary movements, like moving towards the box and then touching it and pushing it and so forth. And for each of these subcomponents of the movement, we want to know actually which reference frame did we use? Was the movement relative to the object, or was it in world coordinates? And then what kind of control did we use in the various directions? So that's the columns there. Did we only use position control or a combination of position and force control? And with that, then we can hopefully reproduce and generalize the movement. So what you see in this little example here is that first we move relative to the object, all position controlled towards the object. And then once we start doing the sliding movement, we push down, so force control in the downward direction and pulling and so forth. So how do we actually determine that? Which of the many combinations we want to use? And that obviously becomes a lot more complex the more possibilities we have. So our insight there was that we can actually take a look at the convergence of the movements of the demonstrations. So the idea is that if we see a converging behavior, that's more likely the correct explanation than if you have a diverging example. So if you take a look again at the example we had on the previous slide, for the first part where we're moving towards the box, if you have the box at different positions and you observe that in world coordinates, then the position is actually going to have roughly this diverging behavior because it's going to different positions in the world coordinates. If you take a look at that from the perspective of the object, then actually we get a nicely converging behavior towards that object. That allows us to pick here the movement relative to the object as the most likely correct explanation of the demonstrations we've seen. And then we can do something similar for forces, additionally taking into account that if you're not in contact, then force control doesn't make much sense. So with that, we can calculate some kind of scores for the different possibilities, and then we pick the most likely one, the highest scores, in this case, these two here. So with that, we can actually reproduce and also generalize the tasks. So in this case, different initial positions of the box here, and you can also generalize it to different sizes of the box. And we can also move this edge against which we pull the object. Then here's a second, slightly more complex example about unscrewing a light bulb and putting it in the trash bin here. I'll switch off my laser pointer for a second so I can skip a little bit through the video. So first the unscrewing movement, and once it becomes loose, we want to move it to the trash. In this case, we were interested in learning actually more than what I was discussing before. So here we assume that we already have some kind of primitives. We still want to learn the attractors, so this composition I was talking about, but also we want to learn the correct sequence. So when do we need to switch? Do we have a loop? So what's the correct sequence, and what are actually the conditions for doing the transition? In this case, it's very important that we get that right. So what you might be able to see in the video is that we're slightly pulling on the light bulb in order to maintain contact while rotating. And then if you imagine that if it becomes loose and we're still pulling, that's just going to start throwing the light bulb everywhere unless it properly detects that the light bulb has become loose. And there we evaluated different types of classifiers to figure out what the correct transition point would be. And again, here we can generalize to different initial positions of the box and the light bulb holder and so forth, and different numbers of rotations. Okay, so now I'm going to switch gears slightly and talk about reinforcement learning. I have no clue who's in the audience. Usually I would ask for a raise of hands, but I'll just go through it quickly to give a very brief wrap up of reinforcement learning also for notation. So in reinforcement learning, we assume that we have some kind of state. So for instance, the positions of the robot arm, we take an action, so maybe apply a motor torque that leads to a change in the state. So the robot moves a little bit, and at the same time, we get a reward, which is some kind of a scalar signal that tells us how well the robot did in this time step. And then we continue doing that. For this talk, I'm mainly going to consider an episodic setting, so a fixed length of steps. We're not so much interested in the individual rewards we get, but we actually want to find a policy. So that's the part in green. So the MacBIM from states to actions that tells us which is the correct or the best action to take for each state. That maximizes not the individual rewards, but actually the expected return, which is a form of a cumulative or summed up reward. To make that a bit more tractable, we usually parameterize the policy. Nowadays, you're typically going to have a neural network in there. The first example I'm going to show you is quite a few years old, so that was some kind of linear basis function approximation. One of the approaches we came up back then is the idea of using reward-weighted imitation, where the idea is that we actually don't want to imitate all the examples we've seen. So in this case, the robot is actually generating the examples itself by trying out various things, but rather focus on the good ones. So to illustrate that, if you have here the mapping from states to actions, the pluses are good examples, the minuses are failures. And if we recombine all of them and just do plain supervised learning and imitate all of that, that's just going to be a mess mixing those up. So what we want to do is to really focus on the good examples and match the successes we had. And then one of the update rules looks something like this, where you have here the exploration that gets weighted by the success, and in this case the Q function or the reward function, the return actually, and this is a normalizing factor, and that's the old policy parameters. So you do a slight update in the direction of what worked well, and you try to not give too much influence on the ones that didn't work that well. So here's a nice little illustration I came up with how that looks like. If we take an example of ball in a cup, where the goal is to catch the ball in the cup. The first trial might end up somewhere there, so that's the closest point in the trajectory. The second trial is a bit closer, so the return is slightly higher. And if we do a weighted combination of the two of them, so take this a bit less into account, we might get something that's in the middle and already quite close. And now we actually have 3 examples we can use to do this success matching. And if you're lucky, then you already get that in. In reality, it didn't work that quickly. One other form of prior knowledge we included there is an initial human demonstration. But if you just play that back, you're going to see in a second that we're still quite a bit off. So by maybe, I don't know, 10, 15 centimeters. The reward function here is based roughly on the distance between the ball and the cup. And after 15 trials, it's already quite a bit closer. After 25, it's going to go, like we saw in the example, a bit on the other side. And then if you try to match both of them, we get something in the middle. After 45 trials, it usually hits the rim of the cup. Sometimes it goes in. And then after 100 trials or so, it has nicely converged and can do it reliably. We tried with my cousin's daughter back then. She was around 10, took about 25 or so trials for her to get it in the first time. For grown-ups, it's usually 10, 20 trials or so. The tricky part is to catch it reliably. So we were in the roughly the right ballpark, but still with quite a lot of initial demonstrations as prior knowledge and these kind of things. And that didn't take any kind of fancy perception into account. Nowadays, if you talk about deep reinforcement learning, you have very high dimensional inputs. So if you take a look at this robot, then you have a camera here, you have the joint encoders, and then maybe a rangefinder additionally. So very high dimensional inputs. You typically have some kind of a bottleneck layer in the reinforcement learning setup in the neural network, which you could call some kind of a state representation. And based on that, you're going to learn the policy or the actions. And now what we started looking into is, okay, so it implicitly needs to learn that anyhow. Can we somehow help the learning approach to make that more efficient, to learn a better state representation for actually learning the policy? So you could include some priors there, like which might also help to learn a more general representation that helps the agent to generalize better to new situations. So concretely, there are a lot of ideas. One of the very typical ones is autoencoding. So you want to be able to reconstruct the high dimensional inputs or observations, again, from this compact representation. If you're talking about reinforcement learning, we also want to optimize the return. So that means we also need to be able to capture everything relevant in this compact representation related to the reward, while some other things might actually be just something in the background that we don't really care about. If you're talking about real systems, then you might also be able to put some kind of constraints on how this representation, the state evolves, that it's some kind of a state dynamics, so that you're only going to take small steps in every time step and these kind of things. So that's the slowness, but also at the same time, you want to make best use of the representational power you have in that representation. So to actually, if you're visiting all different kinds of observations, that should also be mapped to different parts of the state representation. And then actually it turned out that reinforcement learning itself is an extremely good prior to figuring out a good state representation. So to put that in a picture, we have all different kinds of high dimensional observations. We somehow want to map them to a compact state representation. And then you want to learn a Q function if we just have discrete actions that allows us to then reconstruct a policy. And additionally, we have quite a number of different losses, auxiliary losses that help us to find a good state representation. Now we evaluated quite a few different things. So the first setting is just do reinforcement learning only. And the only thing that enforces the state representation is having a bottleneck layer. Can try to learn the state representation and the policy simultaneously. And then actually what we also tried is to alternate between learning the policy and learning the state representation, because if you do it simultaneously, actually quite a few of the losses are somewhat contradictory. So the experiments we did there was on Torque, so this kind of racing simulator. What we did is we trained on a single track, and then what we were really interested in is how general is our state representation. So how well does it transfer to, in this case, the 3 other tracks that have not been seen previously. And optionally, we additionally included some pre-training. So yet again a different track, from which we generated data and which we only use to pre-train the state representation using these auxiliary losses for the state representation learning. So quite a lot of plots here on this slide. The colors again correspond to the 3 different settings of doing reinforcement learning only, learning the state representation and the policy simultaneously, and alternating between them, and then actually also kind of refitting the policy to match the new state representation. What's not, okay, if you just take a look at this one, so just doing plain reinforcement learning without any pre-training, if we test the policy we learned on the training domain, so the one it was trained on, then yeah, it does reasonably well. Not a huge difference between the methods. Where it really makes a difference is when we evaluate it and transfer it to a test domain. So there, just doing reinforcement learning only fails horribly, completely. And learning the policy and the state representation simultaneously actually, in this case, funnily enough, works better than on the train domain, but it definitely helps for the transfer a lot. And then very similar for that, if we additionally include some kind of pre-training, the transfer for reinforcement learning works a bit better, but still including those explicit additional priors on how a state representation should look like helps a whole lot for the transfer. Unfortunately, what we were originally hoping for is that it also helps to make the learning faster directly in the training domain, but that unfortunately didn't seem to help much. So to sum up, explicitly putting priors on the state representation learning at least helps for making the policy more robust to transfer it to new scenarios. So here's a few video clips on the training track. So it was trained on this track and then it tested on the same. It does about the same. The interesting bit is if we evaluate it on a test track. So we don't do any additional training on the test track. We just transfer what we learned on the training track. And then here reinforcement learning kind of works, but it very quickly starts to go off the track and then needs to restart. So what we think happens is that explicitly enforcing the additional state representation learning constraints, it learns what to ignore effectively. So those trees might not be terribly interesting, but what we're really interested in are the sides of the track. And then a bit later, we were, so this was still more or less doing the state representation learning and the policy learning at the same time. And then we started looking into, can we actually do it sequentially? First learn a good state representation and then do the reinforcement learning based on this compact state representation. So what we tried to do is to first learn this mapping from observations to a compact state, potentially with additionally state representation learning, auxiliary loss functions, and then learn this one. So the first phase is just applying plain DQN DDPG, so plain deep reinforcement learning for the whole network and training that, because it turned out that actually using reinforcement learning is a good prior for getting a good state representation. However, then it turns out that for fully fine-tuning the policy, those deep reinforcement learning methods are not necessarily always the best choice. And then the second phase where we really did this split is freeze this mapping from observations to state representation. And then we use CMA-ES in this case to fine-tune the policy, which is then a very small network on top of that. So we evaluated it on various different games and settings. So in this case, the results I'm showing are for this little racing game with a top view. What you see here is the number of episodes and the mean undiscounted return. The goal performance is the best possible performance we could find. And actually, we back well, half a year ago or so, the performance we got was the best we could find in literature for this little game. What you see in black is just doing DQN. It works nicely initially, and then it levels off, and it actually never goes up to this purple line, even if we run it for a lot longer. And then the two different examples you see here is actually the difference is when we switch. If we do the first phase for 2,500 over 10,000 steps, and then move to the fine-tuning of the policy later on. It's still not very sample efficient, but actually doing this explicit split seems to help in getting a better final performance. Okay, and then one last example for learning to interact. So the first parts I was talking about are really complex interactions in terms of friction and forces with the environment. And then for what I now talked about, deep reinforcement learning, it's more the complex high-dimensional inputs. And here is an example of actually interacting with humans. So the task here is to turn this heavy box together with the robot. So we need to make sure that the two agents agree on what to do, and we need to make sure that everything is safe. And in particular, what we were looking here into is how to actually make it also ergonomically better for the human. So we're optimizing a ergonomic score. That's the number here on top. So for instance, here the robot adjusted the height of the object because that's more ergonomic, using a learned model of the human behavior, the human postures, and how the humans react. And that actually helped to make the whole movement a lot more ergonomic by taking this into account as well. Okay, so then now here the promised break to take a few questions if there are any. No.
So no questions so far, but maybe someone was thinking of some. Oh, okay. There's a question from Max. Shall I wait? Maybe I can give Max the opportunity to ask that in real life. You can quickly figure out how to do that.
So yes, the question is: are these results presented? Max, do you want to say it yourself?
I just got unmuted, so I guess I could say something.
Go ahead.
Yeah, so the question is whether, so there's a lot of results on self-supervised learning and learning with auxiliary tasks, I think from Jederberg and all already some time ago. And so the question is, are these methods related in some way, and did you compare to these methods?
So they're definitely related. We did not manage to explicitly compare them. What we compared to is I forgot the first author from Schmidhuber's group, the world models, which are also kind of similar. So yes, they're definitely related, and would be interesting to further look into various ideas and combinations.
Thanks.
So I had a question myself, actually. So you had a couple of auxiliary losses that you added to kind of try to force a kind of decent representation to be learned.
Yeah.
Do you have any insight on kind of which of these was more important than the others, or like kind of the relative contribution of the different losses?
Yeah, we did a quite exhaustive ablation study on switching off different ones and switching on and trying different combinations. Mm-hmm. Unfortunately, it wasn't entirely conclusive. So what turned out is that it helps a lot to have a kind of autoencoder type of loss in there for the performance on the task itself, while that harms the transfer, which is kind of logical because you really focus on the appearance of things, which might be helpful to get peak performance, but then if you have, in this case, a different track, then it might be distracting. And these kind of more physics-based constraints, they seem to help on average in general quite well.
There's also someone, Arnoud Visser, who raised their hand. So I don't know if he has a question, but let's see if I can. Wait, how can I? Oh. It's a little bit. Okay.
There he is. You need to unmute him still, I think.
Yeah. So, oh, okay. But maybe he doesn't have a question, but he raised his hand. So, Arnoud, did you have a question? Yeah, it seems not, I guess. All right.
Okay, then I move on. And if there are any questions at the end, also for the first part, then I'm more than happy to take them. Yeah. Good. So let's slightly switch gears. So the first half, like I was saying, was about robot learning interactions. And now we're going to talk about learning through interactions or interacting to learn. What I didn't talk about when I was showing this little drawing of reinforcement learning is the exploration. So the random actions you need to take in order to discover new strategies or better strategies. So the idea we came up with on how to include human advice during the learning process is to actually include that as a form of exploration. And now I'm going to come back to the ball in a cup example, which I found very cool because that now has picked up a little bit as one of the benchmarks that people like to do. So here now we are learning completely from scratch. We don't have any initial demonstrations. What you can see in the video is Carlos, my postdoc, who is sitting in front of the robot and giving some corrections while the robot is moving, like move more to the right, move more to the left, occasionally, intermittently. And then already after 15 trials, it's quite good. And then after roughly 20 trials or so, we can actually catch the ball in the cup. And we also tried in simulation to learn that from scratch, and it takes like 2 orders of magnitude more trials to learn it compared to having a human teacher in the loop, which is quite impressive, I thought. So now I'm going to switch back to imitation learning, but again, still talk about how to make use of a human teacher in the loop effectively. So the framework we're considering is called Coach. So that's going to look actually very similar to reinforcement learning loops. So we have the environment that is in a state, and we have an agent, the robot, taking an action or that has a policy. But now we have additionally a teacher in the middle. The teacher observes both the state and the actions the robot takes. And then what he or she does is provide corrections in the action space to the robot while the robot is doing the task. So the robot is doing something and you can say, move more to the left here. The original framework was just for using some whatever basis function approximations, and now we also extended it to deep learning. Also there, it's very important to have a good state representation. And here what we started out with is just having an encoder-decoder structure for the state representation learning. So you could, again, pre-train it completely, do it offline, collect a bunch of data from the system beforehand, and train this state representation. However, that can then horribly overfit to some of the things. And if you don't know how to do the task yet, then probably also the data you collect initially is not really representative. So then so what you would do then is indeed first learn the representation and then chop off the decoder and then train a policy based on this representation. So due to the problems I just mentioned, we now switch to actually doing it online. So again, at the same time, learning the state representation and the policy. So here it's updating both at the same time, and effectively the updates happen only when you get corrections, which are actually the most important data points you can get. It looks something like this. So on the left, you see the reconstruction of the state representation. The task here is to push this little whiteboard viper from the table. What you can't really see again is the corrections that are occasionally given. Then quite quickly you get actually a good reconstruction of the image, which is indicative of a good representation. And after 10 minutes or so, then it can completely do it autonomously, which is very quick, at least in terms of deep learning methods. And then after 20 minutes, it really works nicely and completely autonomously. So that's here, the state representation was just really based on the visual reconstruction. That also works for slightly more complex tasks. So in this case here, again, the input to the network, the reconstruction, and the task is to drive this little ducky bot on the right side of the track. And you might be able to see it. Rodrigo, my PhD student, is occasionally giving some corrections via the keyboard. And again, he very quickly learns how to do the task. So to extend that slightly, especially if you're talking about system dynamics, so the dynamic part of that, which is not necessarily directly observable in images or camera images, we added memory. So effectively add a LSTM, so recurrent structure in the model, which then forms a transition model in terms of like reinforcement learning or system dynamics. And the trick we used here to enforce that it actually learns these transition dynamics is to not reconstruct the observation itself, but the observation in the next time step. And then again, based on this combined latent space, that is the state representation, together with the recurrent unit, we use that as the state to learn the policy. So something like this, and we get something like this on a few typical benchmarks. So we only use a single image as an input and not stacked images. And then here you see the next state it's predicting, and then also the what it learns. You can also use that for different types of interactive learning. So Decoach, that's our framework. HGDagger, that's a different interactive learning method. And that works quite well. Here's also a little real example. We have a physical swing up. So the camera image is a bit downsampled. And then again, here, the prediction of the observations. And if I go forward quickly, here you can actually see the real system. And it learns to do it after 12 minutes or so. And you can really see that it's based on the camera by blinding the camera occasionally. Jörg. And as a final evaluation, we tried it on this robot task. So the robot is supposed to pick up some kind of oranges. Here you see the camera input. Effectively, it only sees the part that is shaded in white here. So here, this subpart. So it actually needs to predict where the oranges are going to move. So it really needs the memory there. And then here in the bottom, you saw the predictions. So after 5 minutes, already does the task reasonably well. After 45 minutes, it's really close to perfect. And what's also cool is that based on the state representation we already learned, we can also easily generalize it to different tasks. And here you can see actually the feedback that gets given occasionally. Now it needs to avoid the pairs and move up. And it really learns that within like 3 minutes of training to generalize the agent to this new task. And then here, that's no good robotics talk without a sci-fi clip. So that's really my dream, to make teaching robots child's play. So to sum up, at least my research focuses very much on making robot learning tractable. These kind of experiments are definitely very impressive, but I'd say not very practical. I showed a few examples on learning complex interactions and through interactions. There are quite specific constraints on robot learning, especially that you need to deal with small data and you need to take safety into account. And yes, there are a whole lot of approaches that look into how to best transfer policies learned in simulation to the real world. I'll show you a few examples of what we're working on interactive learning, which turns out to be very efficient and also fairly intuitive for people that have no robotics background. And in general, the big challenges in robot learning are uncertainties and variations in the interactions with the objects, with the environment, different tasks, but also in interacting with humans. That's it from my side, and I hope there are a few more questions now.
Thank you very much, Jens. There's at least one question here in the Q&A, and there's also some questions in the YouTube channel. So the first question is from Elise van der Pol. I will enable her microphone so that you can ask it directly.
Hi.
Hi.
Hi. We already talked about this a little bit in the morning. There's many disadvantages to using autoencoders in reinforcement learning tasks. So I was actually wondering if you've sort of combined these interactive methods with state representation methods that don't require pixel reconstruction.
We haven't tried that yet. It's on the to-do list. So for the first part I was talking about, and also in my answer to Helge's question, yes, we've tried without the explicit observation reconstruction, and that seems to work. So yeah, that's a natural thing to try also in these interactive tasks. And like I was telling Helge, unfortunately, it seems that that's one of the criteria that's actually quite good for getting high performance. And then to answer to Arnoud's question, no, this Duckytown setup is actually not in the Netherlands, but in Chile, where the student came from. We never tried to see how well it works if we train on the real system and then transfer it to the virtual Duckytown world. Yeah, we obviously tried with the learning it in simulation first, but we never tried to transfer it this way around.
Okay, because say Duckytown is a perfect, say, virtual world in between the real life and simulation, and you already showed some of your work in simulation. So I thought, how well does the learned behavior simulation transfer to Duckytown compared to the real world?
I'm not entirely sure I get the question. So where do you want to learn and then transfer it to which setting?
The setting is you showed some simulations, learned behavior on tracks in simulation. Could you transfer that to a track in Duckytown and
I see
then
what you
convert
mean.
that to a track a la the kitty with the data set?
Yeah, so that's a very interesting thought. And to be honest, the type of transfer we did was still within fairly similar scenarios. So it was just different tracks within Torx. So which means that the observations were the same. So the types of sensors we have in there and the type of actions you can do. Because if we think about transferring it from Torx to Duckytown to whatever autonomous driving simulator, then I think that also quite a lot of the sensors and actually the actions you can do change. So you would need to take that into account, either learning that or engineering around it so that at least from the perspective of the network, it looks similar. We haven't tried yet, but that's a very interesting thought on actually seeing how far we can push this transfer. Yes.
Okay.
We still have a question from Max and also some questions on the YouTube channel. So I'll first unmute Max so he can ask his. Oh, I guess you can.
Yes, I have unmuted myself. I think thanks Jens for a wonderful talk actually. So it was really enjoyable. So I have a question. So one of the ways, I mean, you're worried about transfer learning, right? You train something in one domain and then you want to move it into another domain and it should still work.
Yep.
So one way, in my view, to do that in normal sort of learning is to also model the explicit physics of the world. In some sense, the transition functions in the MDP. Of course, there's a physical model that you could implement there, or you could at least sort of have a parameterized model that tries to model the physics and then fit it somehow. Is this something that you have tried, and is it helpful at all, you think?
It's definitely helpful. I mean, then depends a bit on what exactly you do. You get into the whole domain of sim to real transfer, which is very active at the moment. So yes, we've tried that. In particular, what we tried a while ago is to use some kind of a baseline rough model of the real system and embed that and explicitly use it, and then only learn an offset model on that. So kind of a model that explains the differences between our simplified model and the real world. And that made it so we could get roughly 90% of the performance by using only 10% of the data compared to learning it completely on the real system. So that definitely helps. I've worked a little bit on this kind of system identification model learning, but parameter identification, but I've not yet combined that with reinforcement learning or do that in the reinforcement learning loop, but that's definitely a very interesting idea. And I think, yes, indeed, it will help to a lot to do the sim to real transfer. You always have to be careful that you don't overfit the policy to some little modeling errors in your approximated dynamics, but there's some ways to make that more robust. So yes.
All right.
Short answer, it definitely will help, I think.
Okay, great.
So there were two questions on the YouTube stream as well. So one very short one, how many light bulbs were destroyed during the initial experiments you presented?
So in the end, we put 5 on the head of the PhD student that were destroyed.
All right, so this kind of the safety, it's not there yet, but it wasn't too terrible. It wasn't like a million, I guess.
No, it wasn't like a million, and we caught quite a few. Yeah.
All right, and then another a bit longer question. The previous one was by user Fly Surreal, by the way, and this one's by user Moore. You mentioned that the teacher gives instructions in the action space, but how to let the human give instructions when the action space is direct motor control, like motor current?
Yeah, that's definitely one of the tricky questions. So this method assumes that the human is able to give meaningful corrections in the action space. And indeed, if you have very fast dynamics of the system or very unintuitive low-level commands, or what also gets tricky is if you have very high-dimensional actions, because it turns out as a human, you can maybe control 2-3 dimensions at most, then it gets tricky. So one way around that is to actually use a little module in between that you give a correction on a slightly higher level. So whatever correction in the position, and then you have some form of a controller that translates that to the direct lower level actions. The one what we started to look into now is to actually give corrections in the state space, and then have a learned effectively inverse dynamics model that maps it back to the actions you would need for the correction.
Both of these ideas, are they work in progress, or do you already have something published on that?
So the last part I was talking about, using the inverse dynamics model, that's work in progress, and we're probably going to submit it to Coral or something.
Mm-hmm.
The other one that's published, but not in the deep version.
Right. Okay. Thank you. I guess I'll take a look at least at some of those works. And yeah, thanks again for being here today and giving a very nice talk. I think it's very much appreciated by everyone, and I think yeah, it also gave everyone some new research ideas. Maybe at least I'm kind of thinking already about you know, how can these things maybe be improved further, or kind of what are alternatives and so on. So there's no more questions. We're also reaching the end of the time. So yeah, thanks again. And I think we shall stop the meeting here unless there's any last comments you want to make. Or...
Yeah, thanks a lot for having me. It was a lot of fun. If you have further questions, you can see my email address and website there. Just shoot me an email.
There's still one question in the Q&A. Will the presentation be published? There is, I think, in the YouTube channel, it will be available afterwards to look it back. And we'll kind of, I think we'll try to make a recording available as well, but we have to see how technically to best do it. But at least for now, it will be available on YouTube as well.
I can share a PDF version of the slides if you like.
Oh, that's very nice. Yeah, I think there was a problem with like, I think both in the webinar and in the YouTube channel, it was hard to see the videos. So I'm not sure, yeah, if you make a PDF, and of course we also don't have the videos.
I can try to put links or something in as much as possible.
Yeah, okay, that would be really great. Okay, well, then thanks again, and I hope we meet again live very soon when everything is getting back to normal a little bit. Yeah, hope to see you soon in other circumstances. All right, goodbye.